Okay, so so L1 equals L2 is it's called the principle of conservation of linear momentum. Where L is the mass times velocity, and the most important thing is this is valid only if the linear impulses to the system are zero. In other words, if there's no external impulse to the system, then you can say L1 equals L2. One example we had done previously was if you have two balls colliding with each other, then for the entire system, right? If you take the sum of the two systems, then linear momentum is conserved. However, if you start analyzing the system individually, then linear impulse is not conserved, because for the individual system, there's a force acting on those on the individual system. But if you combine them, then the in linear impulse which causes them to interact when they collide is internal to the system and will not show up in the equation. So it's true for two colliding balls as a system, but not for the individual balls. An example, the principle of conservation of angular momentum states that the angular momentum before collision or motion so instance 1 equals the angular momentum afterwards, and it's called the conservation of angular momentum. H is, as you know, it's I omega. Well, I, you've got to be very careful of how you define I. I is Ig omega, or it could be IIC omega. This is valid only if angular impulses to the system are zero. So there shouldn't be any external angular impulses. Okay, in fact, if there are external impulses, then you have to use the principle of angular impulse and momentum. Remember, we did this in the previous class where h01 equals integral m0 dt equals h02. So you'll apply something different. So that's it. So once you have identified if there's no angular impulse or linear impulse, you can apply those two equations. So let's see what sort of problems fall under this category. Okay, this is a very standard physics demonstration. I wish we had that kind of a table. Essentially, if you stand with dumbbells on a table which is rotating, actually you can do it if you have that chair there which swivels. You could do it on that. You need dumbbells or something heavy. What you do is you spin. When you spin at a certain speed and you keep the dumbbells, keep your arms extended, and then when you spin, you suddenly move them closer, and you see that you start spinning faster. Okay, we'll solve a problem where we'll see that how that comes from equations. Then I have a video which demonstrates this principle. The 80 kg man is holding two dumbbells while standing on a turntable of negligible mass, which turns freely about a vertical axis. So this is how he is spinning. well, he is shown the other way. It's fine. When his arms are fully extended, the turntable is rotating with an angular velocity of 0.5 revolutions per second. So in this position, I'll call it omega 1. His speed is 0.5. Determine the angular velocity of the man when he retracts his arms to the position shown. So you got to find what is the angular speed when his arms are retracted. When the arms are fully extended, there is a certain geometry associated with him, right? That's what is given the next, and then there's certain geometry when he's extended. So I'm going to try to draw that geometry instead of trying to read it up. I'll write it as I read through it. So when his arms are fully extended, approximate each arm as uniform 6 kg rods having a length of 650 mm. So assuming his arms are so, they are of length 0.65 meters, and of mass 6 kilograms, so 6 kgs. Let me move this. I guess it's okay. And his body is a 68 kg solid cylinder of 400 mm diameter. So his body is a cylinder of weight 68 kgs, and I'm going to write the radius instead of diameter because we will use the inertia, which is written in the form of radius. So radius is 400 mm. That means so diameter is 400 mm. So radius is 0.2 meters. Okay. And of course, this doesn't give you the dumbbells in this, right? So I need to put the dumbbells here. So the dumbbell is right here. We assume that those are point masses. Each dumbbell consists of 2 spheres of 5 kgs of negligible size. So when the size is negligible, you can treat them as particles. So let me put a particle here. And the weight is, well, it's 5 kgs for each of those balls. So there are 2 balls which make a dumbbell. So it's going to be the 2 spheres. So it's going to be 10 kgs. Right, because the 2 of them. Okay, so that's on the one side. You'll have the same thing on the other side. Okay, that's what happens when the arms are fully extended. When the arms are retracted, assume the man is a 80 kg solid cylinder. So axis remains the same. 80 kg cylinder of 450 mm diameter. So the radius is half of 450, which is 0.225 meters. Okay, and of course the dumbbells are going to be here, 10 kgs. So that's how he looks when his arms extended. That's how you approximate his geometry when his arms are fully retracted. Okay, so the question is, what principle do we apply? Well, in this case, since if you look at the complete system of the turntable, they have said the turntable is negligible mass, and the person, then there is no external force acting on the system, so no external impulse. So that will equate to 0 linear impulse and 0 angular impulse. Okay, so we can apply the principle of conservation of momentum. So in this case, we'll apply the conservation of angular momentum because we are interested in angular speed. Conservation of angular momentum. So h01 when its arms are fully extended equals h0 after his arms are fully retracted. So initial, this is 1, times omega 1 equals I2 omega 2. This is the instance 2. So it all boils down to finding I1 and I2 for those geometries. So let's find I1 and then find I2. I1 consists of 3 parts. Well, 5 really. 1, 2, 3, 4, 5. But I'll find inertia for this, this, and this, and inertia for those two is just twice of the 2 arms. So so it's going to be I body plus I arms plus I dumbbells. And everything is about the axis. Let's call those axis O. About axis O. So let's find I body. That's simply, so inertia of a disk, of a cylinder about an axis this way is same as the inertia of a disk. It's half mass. Let me write the mass here. 68 kgs times the radius square. Okay. So I need to write the inertia of the arms. I just multiply it with 2 because there are 2 arms. So the inertia of the arm is a cylinder, but for the body, the cylinder was facing this way, and so the axis was that. For the arms, the cylinder is this way, and we need to find inertia about this axis. So it's different, right? Inertia about this axis, so rotating. Inertia about this axis, so rotating. So inertia about this axis is not half mr squared. It is 1 by 12 ml squared. So 1 divided by 12 times the mass, which is 6 kgs, times the length, which is 0.65. Okay, but that's the inertia about G. We need to find the inertia about O. So that's going to be mass times the length, the distance from G to O. So that's going to be half of 0.65, and this distance is 0.2. So this is 0.2 as it is shown here. So it's 0.2 plus half of 0.65. That is going to be 0.525. Is that right? Yeah, 5 to 5. So 0.525 square. Okay. And then finally, I need to find the inertia of the dumbbells. Now there are 2 dumbbells. I'm going to put twice. Since they are particles, all I care is the mass times the distance from the axis of rotation. So the distance is going to be 0.65 plus 0.2, so 0.8. So each dumbbell is 10 kilograms times the distance from this point to O. So it's going to be 0.85 square. So if you do the math on this, comes out to be 19.54 kg meter square. Next, we find the inertia of this system. It's much simpler than that one because now only there are three geometries. So for the cylinder, it's going to be I body is going to be half times the mass, which is 80 kgs, times the radius square, 225 square, plus the dumbbell has 10 kgs, and it's a distance of 0.2, I think. That's it. Oh, sorry, it's 0.3. My bad. See this? 0.3. 0.3. So 0.3 square. Right? Since there are 2 dumbbells, I just put 2. So that comes out to be 3.825. Okay, so you're all set to solve this. So I1, omega 1, so I1, 19.54 times omega 1. Now, angular speed is given in terms of revolutions per second. I'll just write the answer in revolutions per second, but you can convert to radians per second if you want to by multiplying it with what? 2 pi, right? So I'll write it as 0.5. This is revs per second equals 3.825 times omega 2, which is the unknown. So if you solve for omega 2, you get 2.55 revs per second. Okay, if you want, you can also write or omega 2 is 2.55 times 2 pi radians per second, because one revolution is 2 pi radians. Okay, you can write either way as long as the units is right. It's fine. Okay, any questions on this? Any questions? Okay, so here is a video demonstration Friday. That will be the 2 review days. Okay, the 2 kg rod ACB supports the 2 4 kg discs at its end. So this is 4 kg, 2 kg. If both discs are given a clockwise angular velocity of 5 radians per second while the rod is held stationary and then released, determine the angular velocity of the rod after both discs have stopped spinning relative to the rod due to frictional resistance at the pins A and B. Motion is in the horizontal plane. Neglect the friction at pin C. Okay, so this is maybe slightly difficult to understand what's going on. So initially the rod is horizontal, it's at rest. Those discs are given speeds of 5 radians per second. It is spinning fast. What happens is, because there's friction between at pin A and pin B, there's going to be interaction between the spinning disc and the rod. If there was no friction, they will just keep spinning. But since there's friction, they're going to interact. When they interact, this rod is also going to start spinning. So eventually there'll be a time when everything spins at one speed. So this disc has 0 speed with respect to the rod. In other words, it's at rest relative to the rod, but the entire system is rotating. So the relative speed is 0, but the absolute speed is non-zero. You got to find what is that angular speed which the whole system spins about. Since C is frictionless, you don't have to worry about friction about point C. So since C is frictionless, well, what we'll do is we'll apply the principle of conservation of momentum about angular momentum about C, because even if there was a force at C, which there would be, right, if you draw a free body diagram, that force will not show up in the equations, or the angular impulse is going to be 0 if you take moment about C. So let's choose this axis and state the principle of conservation of angular momentum. HC initially equals HC final. So I1 omega 1 equals I2 omega 2. Well, really this is summation here, because there are 2 masses. There are 3 masses. Okay, so let's start with the first instance when only the disks are spinning. So we have 4 kg disks. Their radius is 0.15. So mass times r square. But since it's a disk, the inertia is mr square divided by 2. I disk is okay. But there are 2 disks, so it's twice. Times the angular speed, which is 5. Okay, equals I2. So now we're going to find inertia when the whole system spins about c. So now we'll have to find inertia of the, first let's start with inertia of the rod. That's 1 divided by 12 times the mass, which is 2 kgs, times the length, which is 0.75 and 0.75, 1.5 square. This is I rod. Plus inertia of the disk, so it's half times 4 times 0.15 square. But now the disks are not spinning about A and B, but they're spinning about C, the axis C. So I need to apply the parallel axis theorem. So mass times the distance from A to C, which is 0.75 square. Okay, since there are 2 disks, I'll put 2 here, and then omega 2 is the unknown. Okay, so everything except omega 2 is unknown. So we can solve for omega. It comes out to be 0.0906 radians per second. So starts off with 5 radians per second, right? Because the inertia is less, and now the speed decreases because the inertia increases. Okay, any questions on this? Okay, last question. The 10-gram bullet. Let me just write it in kilograms. 0.001. So it's 0.01 kgs. Having a velocity of 800 meters per second, is fired into an edge of a 5 kg disc. 5 kg disc. Determine the angular velocity of the disc just after the bullet gets embedded into its edge. Also calculate the angle theta the disc will swing when it stops. The disc is originally at rest. Neglect the mass of the rod AB. Okay, so when the bullet hits the bullet is going at a very high speed. It's going to be it's going to hit and penetrate the disc, because of which the pendulum, so-called pendulum, is going to have a velocity, right? You're going to find that velocity, and then because it says velocity, it's going to swing at an angle and come to a stop. You're going to find that angle. Okay, so how do we solve this? Well, first thing to notice is that if you consider this system or draw a free body diagram of it, when the interaction is taking place, there would be some impulse over here. Draw that. A vertical impulse and a horizontal impulse. This is at impact, right? So can we apply the principle of conservation of linear impulse? We cannot, because there's h and v. However, we can apply the angular impulse if we choose the point to be A. About A, the angular impulse is going to be 0, or external impulse is going to be 0. So we can use conservation of angular momentum. Okay. H initial about A equals H final about A. Initially, the pendulum is at rest. The only thing which is going to have a momentum is going to be the bullet. So mass of the bullet, which is 0.01 times velocity of the bullet times, let me just put it in this form. Okay, I'm going to run out of time, so let me just write it this way. Mass times velocity times the radius, which is 2 plus 0.4, right? Because this distance is 0.4. So what I've written down effectively is mass times velocity times r. So r cross mv is the angular momentum due to a particle. Equals the angular momentum after the bullet gets embedded. So now the system consists of the bullet, which now you can assume that the bullet gets embedded here, can be embedded here, here. Okay, where it gets embedded matters because the inertia is going to be different, right? If it gets embedded here, the inertia due to this is going to be due to this length. So if it gets embedded here, we need to find the inertia about here. So it's not given where the bullet gets embedded, but we're going to assume that it gets embedded here. That's how the book does it. And apply, well, try to find the distance. So if this is 2.4 and this is 0.4, then this length can be found by Pythagoras theorem, which comes out to be, well, 2.4 square plus 0.4 square equals 2.43. So the momentum after it gets embedded is, the complete system is going to have one speed. So I need to find inertia about A. So inertia about A is due to the disk. So mass of disk is 5 kgs times the radius square divided by 2. This is I disk. But the inertia is about A. So I need to use the parallel axis theorem. So mass times 2.4 square times omega plus the angular momentum due to the bullet. So it's going to be 0.01 times 2.43 square. It matters in the inertia. Let me write it here. So 0.01 times 2.43 square times omega md square inertia of bullet. Does that answer your question? It's a particle here. So inertia of the particle about that is going to be md squared times omega. Anyway, so I'll just write the answer for omega and then solve the rest and post it. So omega, if you solve for omega, it comes out to be 0.65 radians per second. Okay, so I'll see you on